Hi everyone, in this video I'm going to be solving this very cool problem that came up on the PUTNAM 1984 contest. Here's what it says: find the minimum value of this expression u minus v whole square plus the square of root of 2 minus u square minus 9 by v. So this whole expression for u in 0 to root 2 and v greater than 0. So we have this expression in two variables, two real numbers u and v, and we have to find the minimum value of this expression given that u lies between 0 and root 2, and that is necessary because you want this term here to be a real number and it has 2 minus u square under the square root sign. So you want u to be less than root 2, and we are also told that v is greater than 0. So given these constraints, we have to find the minimum value of this expression. Now at first glance, this expression seems really complicated and weird, and it seems like finding the minimum value of this expression would be very hard. In fact, if you take the standard approach of finding the minimum value of an expression, this would actually turn out to be a bit hard. There are two variables here. You would have to perhaps use partial derivatives and then try and find the minimum value. But there is actually an alternate and very elegant way to finding the minimum value of this expression. And I would urge you to pause the video and think about that for a bit before you go forward and see how I'm going to solve it. Well, my solution, or the elegant solution I should say, rests on the fact that this expression here has a very specific structure. It is something minus something square plus something minus something square. So it actually resembles the structure of the distance formula. And what is the distance formula in coordinate geometry? So if you have 2 points in the coordinate plane, let's call them x1 comma y1 and x2 comma y2. And if you take these 2 points and the distance between them, let's say, is d, then the distance formula tells us that d square is given by the difference of the x coordinates. So that's x1 minus x2 square, and then you take the difference of the y coordinates, so y1 minus y2 square, and then you add them. So d square is given by this expression here, and that is the distance formula. And now if you notice the structure of the expression on the right side, you find that it resembles the structure of the expression given to us. And therefore, if I think of this u as my x1 and this v as my x2, and if I think of this term here, which is root of 2 minus u square, as my y1 and 9 by v as my y2, then I can see that this expression suddenly starts resembling the distance formula. And this expression is actually giving me the distance between x1, y1, where x1, y1 is u comma root of 2 minus u square. So let me write this here. So x1, y1, my first point, and let's call that point P. x1, y1 is u and root of 2 minus u square. So x1, y1 is a point, or P is a point whose coordinates are u and root of 2 minus u square. And the second point, and let's call that Q, will be x2, y2, and that will be x2 is v and y2 is 9 by v. So v comma 9 by v. So that was the crux move here. That was the important step here, recognizing that this expression is actually nothing but the distance square between this point and this point in the coordinate plane. Now, what is this point really? U comma root of 2 minus u square. What is this point? Where do you think this point is going to lie? Well, once again, the structure should tell you where this point lies. If you take the x coordinate and square it, and you take the y coordinate and square it, and you add those two, you will get a constant. So the x coordinate here is u. So x coordinate of p is u, and the y coordinate of p is root of 2 minus u square. And from here, if you square x and square y and add them, so x square plus y square will be equal to u square plus 2 minus u square. So, u square plus 2 minus u square, which is equal to 2. And that we immediately know is the equation of a circle centered at the origin with a radius of root 2. And therefore, this point u comma root of 2 minus u square, this actually lies on a circle centered at the origin with radius root 2. What about this one? V comma 9 by v. So, the x coordinate here is v and the y coordinate here is 9 by v. And now we can immediately see that if we multiply these two coordinates x and y, they'll give us v times 9 by v, which is 9, which is a constant. And that means that the product of the coordinates x and y of the coordinates of this point x y is a constant equal to 9. And once again, this equation is very familiar to us. It's the equation of a hyperbola. So, immediately we realize that this second point lies on a hyperbola xy equal to 9. So, that's it. We are done with the heavy lifting of the problem. We have realized that the first point P with these coordinates x equal to u and y equal to root of 2 minus u square, this lies on a circle centered at the origin, radius of root 2, and the second point Q, which has these x and y coordinates, it lies on a hyperbola that is xy equal to 9. And we have to find the minimum value of the distance between P and Q. Actually, we have to find the minimum value of the square of the distance, because the expression given to us resembles d square. So, we have to find the minimum value of the square of the distance between these 2 points. So, what I am going to do now is draw these two curves. So, here is my coordinate plane x y. Let me first draw the circle x square plus y square equal to 2. So, that is centered at the origin with a radius of root 2. So, here is that circle, and this is x square plus y square equal to 2. And now, and P lies somewhere, the first point P, which is u comma root of 2 minus u square, it lies somewhere on this circle. And my second point Q, it lies on the hyperbola xy equal to 9. And we were also told that, if you remember the original constraint, we were told that v is greater than 0. So, which means that the x coordinate of the point on the hyperbola is greater than 0. So, I just need to take the right side of the hyperbola, the segment of the hyperbola that exists for the positive values of x, and that would be something like this. So, this would be xy equal to 9, where x is greater than 0, all right. And now we have to find the minimum distance between a point on this curve on the circle and a point on this hyperbola. And you could once again become very analytical about it and try and solve it by doing a lot of algebra. But actually, using the symmetry of this figure, you can immediately see that the minimum distance between these two curves would happen along this line, which is the line x equal to y, because both of these curves are symmetrical about this line. And if you were to draw tangents at this point and this point, those tangents would be parallel. And if you want, you can actually go ahead and prove that. But I am just going to directly use my observation here and claim that the minimum distance would happen when P, the first point, is over here, and Q, the second point, is over here, and this would be my minimum distance. Now, what is this distance? So, and once again, remember that I have to find the square of the distance. So, let's call this d. So, I have to find d square. So, what will that be? So, this point here, what will this be? So, this will be, you have x equal to y. So, the coordinates here of P are equal, and we also know that x square plus y square is 2, and that immediately tells us that this point must be 1 comma 1, because 1 square plus 1 square is 2, and the coordinates x and y coordinates here are equal. And what about the coordinates of Q? So, you want their product to be 9, but you also want the two coordinates to be equal. So, they must be 3 and 3. So, the coordinates of Q must be 3 and 3. And now we are done. Now, we just find the distance between these 2 points. So, d square will be equal to 3 minus 1. So, that is 2 square, which is 4, plus 3 minus 1, that's 2 again, square, which is 4. And that means d square is equal to 8. So this is the minimum, 8 is the minimum value of d square, and that is what we were supposed to find. So that concludes our solution and gives us the answer as 8. So what I really did here, the crux move here was to recognize that this expression actually resembles the distance formula, and it resembles the distance between this point here and this point here, and then just recognizing that this point is actually a point on the circle x square plus y square equal to 2. This point is a point on the hyperbola xy equal to 9. So I hope you enjoyed this solution. Let me know what you think in the comments. Thank you.